Swayam Prabha. Digital India. Educated India.
Welcome to this NPTEL online certification course in structural system in architecture. So, we are in the module number 8 and it is the spatial structure is the module name, and we are in the fourth lecture of module number 8. In continuation, it is the 39th lecture and we will be discussing today the structural systems of high rise building part 2. So, we will cover those concepts today. We will start with some small introduction, then we will go to the exterior system. If you remember, in the last lecture we have discussed the interior system. Exterior system is mainly based on some of the tube systems, and also we will discuss all the type of tube system. And in the learning objective, we will have that the structural concept of the exterior system we will going to develop. The outline that one, and we will discuss the development of the tubular system. So, initially in the introduction, let us first talk about a gentleman who has been born in Dhaka, which is in Bangladesh. Fazlur Rahman Khan, 1929 is the birth year, and he is no more. He died in 1982. He is a Bangladeshi American structural engineer, and he has developed a lot of structural configuration for the high rise building in the 70s, in mid 60s, 70s and all. And he was known to be the father of the modern skyscrapers from the point of view of a structural engineer. The Efar Khan has developed the tubular and this exterior kind of system of his own, with some of his projects or so. So, what he told that see, as and when you go high, if you think of you want to go 50 storied building, 60 storied, 80 storied building, probably much more, then there are two load, as you always we are saying from the last fourth week lecture or so. It is the gravity load, which is the dead load and the live load, and there is a load called the lateral load, which is basically wind and sometimes earthquake. So, both the load has to be taken into account, and we have to actually design for that. So, there are some typical members, or there are some typical design fundamentals you have to adopt, and finally, we have to do some kind of a structural detailing, structural output to take care of the gravity and take care of this lateral load. Now, if you just see that if I increase the height of the building, it is I have mentioned in the x axis, then what is the proportionate amount of the steel required, the average weight of the structural steel required to take care of the gravity load, and how much is the average weight of the steel is required to take care of the additional, you may say, that is take care of the wind load or the earthquake load. So, if you see, the gravity load requirement is linear, obvious. If you are increasing the building height, number of floors, your total amount of the gravity load is increasing, total amount of the load of your the live load is also increasing, and that is added up one after another, and gradually the floors, which is bottommost floors or the towards the bottom floors, the structural systems like columns and all are definitely you need thicker sections, you need more weight of the consumption of the steel. But if you see the increment of the floors and the amount of the weight of the structural steel which is required to support that particular load is linear, it is just linear. If you increase 2 floors, whatever increment, if you increase 4 floors, it is 2 times more of increment. But it is not so simple or not so linear in case of the lateral load. The lateral load is not very linear. Actually, see, if you see the wind load, it is parabolic. If you go high, the wind pressure is increasing, parabolically increasing with the height. So, in totality, the moment that is generated, the shear that is generated in the base or the sway that is be generated in the top floors will be very high, or in case of that it is non-linear. So, it is going to be higher and higher, it may be a the quadratic or maybe the cubic form, it is going to high. And as and when it is going to high because of the wind, the top, your amount of structural steel consumption to take care of that particular wind is also going to be high. So, that line is non-linear or it is kind of a parabolic line. So, these the black or this firm line, I may say, is this is your additional structural requirement of the lateral load. So, this one. So, the amount this initiate from this point on, this is almost okay, they are going almost okay parallelly or whatever. After a certain height of the building, this is flying, this particular amount of steel required for the lateral load is just flying, shooting up, and the extra amount of the steel you require. So, this is the extra amount of steel in the patch I have shown. So, this extra amount of steel, the F.R. Khan told it is the premium for height. So, you have to pay extra, you have to invest extra amount of steel as and when you want to go high, and that extra amount of steel is because of the lateral load resisting frame. So, the thought process changes, and now we have to see that how this extra amount of steel can be controlled. You cannot control fully, but can be controlled somehow, so that this can be economically used. So, the exterior system came into the picture. Interior has a problem, interior system has a problem, because the interior core is fine, that is going to take care of your the lateral load resisting frame, but the total building has to be seen in a different way, and that has been taken into account. The major part of the lateral load resisting systems located in the outside or the perimeter. So, it is desirable to provide a lateral load resisting system to system component as far as possible the perimeter of the wall to increase the structural depth, which is very important. See, again you imagine this particular building is a cantilever out from the mass from the ground. So, you need to increase the total the structural capacity or the flexural capacity of the building. It is going to bend because of the load. So, you have to increase the depth. If you remember, in the deflection of the beam we have discussed, the depth increase the moment of inertia I, and that increase the EI, that is the flexural rigidity. So, if I increase the depth of the building, structural depth, non-structural depth I am not talking about, structural depth of the building. So, what is going to happen for that? So, your total building will act as a cantilever, not only the core. So, these systems which I discussed in the last lecture, in interior system, it is only the core which are going to be act as a backbone or the structural element that will taken care of by the system, that is the load resisting, the lateral load resisting system. But no, here we distribute the structural steel, the structural element at the perimeter. So, what happened? The building, the depth, the structural depth is increased, the I, the moment of inertia of the building. If you consider that building is a beam standing in the upstand beam like this, is increased. So, that will take care of that. That will take care of your lateral load resisting systems also. So, he considered the tubes, the F.R. Khan considered the things a tube, and the major part of the structural influence, the structural consumptions are put into the perimeter area. So, that is why that is called the exterior systems, and the tubes are his creation, the tubes and tubes and tubes. So, different type of tubes he has created. It can be defined as a three-dimensional structural system utilizing the entire building perimeter resisting. I have just told you that is act as a whole building is your beam. So, it has different type of classifications, further classification. The first one is the frame tube system. The frame tube system has further typical types. Almost everything was developed by the Fazlur Rahman Khan. The frame tube, the breast tube and then the tube in tube and the bundle tube system. And then further the modern era, from that we nowadays thinking of to go further more high with some kind of a hybrid kind of systems or maybe exterior systems with some kind of innovations and all, known as the diagrids, the space truss structure, the superframes and the exoskeletons. So, the frame tube structure as depth from the point of view, the building is actually constructed in the perimeter closely spaced beam columns, sorry, and the spandrel beams are the deep beams. So, practically in the perimeter you do not have anything, no amount of not much amount of places can put the windows or so, I mean those glasses or so. It is almost 1/3 of the floor is taken care of by your beams, the height and the columns very close by. So, depending upon the structural geometry and the proportion, exterior column spacing will be 5 to 15 feet, 1.5 meter to 4.5 meters, that close. But remember that close spacing is only in the perimeter, not inside the building footprint, that is almost free of column. And the spandrel beams which is having depth is 24 to 48 inch. So, that is almost about 600 to 1200 millimeters. So, if you take average as a 1 meter, so almost 1/3 of the height of the depth of the habitat room is taken care of by your beam. But that is again, please remember that is again it is in the perimeter. So, you do not have to worry because of the actual areas, actual floor plates area, the beams are slick. So, now you imagine this huge structural influence in the perimeter with the spandrel beams and the closely spaced columns create a box, huge steel box or concrete box, and that box is now it is firm and you can go high, because this box itself is a structural system. So, something like this, there is a core definitely, shear core is required to take care of that, and shear core is actually house all those lift and the staircases and some of the this vertical transportation area. So, this deep beam, the spandrel beams connected by the columns from the tube and the periphery closely spaced columns are also there. So, based on that there are a lot of construction came, lot of building came. One of the building 1971 WTC New York, that is the World Trade Tower, World Trade Center New York, which building you know it is no more. After that 9/11 strike by the terrorist attack, this building was destroyed. So, this building was not constructed, but it was actually structural design done by the Fazlur Rahman Khan, and it is one of the building, can be classical building you may say, if you see the frame tube structural point of view. So, buildings look like box here. The next is the braced truss system, where nothing there is small improvisation was created. Instead of going with this the spandrel beam and the column, which create a kind of a square or rectangular kind of a frame, they introduce the diagonals also, two diagonals also introduced, and because of the two diagonal introduction, this particular the frame, which is the outer frame, is much more stiff, as we understand. If you just want to push a without any kind of a diagonals, if you want to just push this particular square, it can be easily made rectangles. We have discussed in our truss lecture in the week number 5, and if you put the diagonals, then one of has to be, if you want to push, you cannot easily make it rectangle to rhombus or maybe square to rhombus. because one of the diagonals has to be under compression and the another has to be in the tension. So, that is very difficult. Another one is that is one of the important I have written probably. Yes, this diagonal participate in dual role action. So, first role is I have told you that it make you rigid, much more rigid. The second role it can actually channelize the load. You can gravity load can also be channelized. So, it has to be the flow of gravity load is very distributed, and it is not only through the columns, some of the loads can also channelized through the diagonals. So, this channelization of the load is possible, and lateral load point of view would become much more stiffer as the diagonals are introduced. So, this is the whole. Now, the thing is that the in nutshell, if I say, the concept is that the frame tube was there, which was you have seen this 2-3 photograph of these 3 buildings, WTC and all. Now, you put some belts or this kind of diagonals and wrap it up in the wrap it up in the as if these boxes are wrapped up, these tubes are wrapped up, much more stiff, much more rigidity, same footprint, but there are much more the I values or the moment of inertia increases like anything. So, those are the some of the structure that came interesting. It is also eye soothing instead of going with a box kind of a structure. Some diagonals gives you some breaks. We architect likes that one, that create a kind of a break the monotony. It creates some kind of interesting features in the building and also creating kind of a play in type in the elevations, and this particular gives you some kind of contrast in visual contrast. In the background there are the grids, the horizontal and the vertical grids, and in foreground there are some inclined lines creating kind of a visual contrast. So, also help in the break down the monotony and increase the rigidity structurally. The tube in tube, the next one, the tube in tube. So, you think of a tube and there is another kind of a tube which is inside the tube. So, there are now instead of the one such system, there are you put another kind of a tube in that, the structural rigidity is going to increase and the central tube may go little bit higher and the outer tube or the bigger tube can be little lower. So, that is the concept of the tube in tube kind of a system. Okay. This tube in tube resist, I mean that is there, and we let us go to that. Yes, this is the tube in tube. So, you have different type of tube in tube systems. So, you have a central this is one tube where there is influence of this the footprint is much more, the influence of the structure is structural elements are much more, and this is the outer tube which is here, and the outer tube goes till this and the inner tube goes till that. So, this is the tube in tube kind of a system. So, there may be one tube, one interior tube, there may be 4 such exterior tube, one interior and another shear core, or that may be in. So, you can now play with different geometrical forms. There may be 3 tubes, 1, 2, 3 concentric circles, concentric ways. So, different types is possible. This actually comes again, see the frame tube structure WTC is a box, is a tall kind of a box. Here at least you can play with some kind of a formation, some kind of a geometric formation. Maybe the central one is high, the side two are low, sometimes side two are high, central low. So, there can be some kind of the formation possible. So, tube in tube is further enhance the taller building, further enhance the beautification of the building in other way around, and also in the ground plane it strengthen the building better way, because there are 2 rings possible, not only the outer ring, there is the inner ring also possible in this particular system. If you cut a banana tree, you will see this particular things are there. The banana tree, when it grows up and it has a tube in tube. So, the cell or the skins are like a tube, and then there is another tube. So, those are the, you can say it is the inner tube and the exterior tubes are concentric, and that is going to happening like that. The last one in the tube system is the bundle tube system. It is very wonderful the development of the Fazlur Rahman Khan, and it is the in tall buildings the large floor areas and the simple frame tube system is very uneconomical, as I have told you, because it is one tube has to take care of your whole. So, to overcome that a symmetrical grouping of the tubes has been thought of, symmetrical grouping of the tube, and this grouping of the tube is thought of such a way that it symmetrically cut in different levels, and the load flow is very symmetrical. The further this grouping of the tubes called the bundle tubes. So, there are 3 bundles, there are 9 bundles, there are 7 bundles, like that, there are different bundles of the tubes, and those tubes are the creating those tubes as the major footprint, the major type of the clustering, and that takes up the structure. So, let me explain that one. Suppose my the ground floor, the building footprint is a square. So, what I have done is that you may divide the square into 9 smaller square, okay? 3 3s are 9. So, one square can be 1/3 in the length sides, and you can cut down. So, you have create 9 such square, and in that 9 square you can imagine there is a tube of this L type of tube. This is tube number 1, which was symmetrically opposite side. There is a tube number 1, which is this one, tube number 1 is this one. Please remember that tube is not a square or rectangular tube, that is a kind of a tube which is L shape. And there are tube number 2, which is this 2, which are again symmetrically located diametrically opposite inside, and that tube is a square tube, and that tube will go till the intermediate height. So, this tube will go the L tube, if it is go till this, the second tube will go till this and cuttle, and the central tube, which is the T3, which is again a square kind of a tube of similar size, which will go the highest point and symmetrically cut down. So, your building is grouped, and the bundle tubes are like this is called bundle tube system. The tubes are bundled. So, through the sections of any side you can see like that, or it will grow up like that. The central one will go till the top, and the symmetrically cut down like that. So, if you see the Sears Tower, Chicago, which was the tallest building once upon a time, before I think Petronas Tower. Now, it is Burj Khalifa, which is the tallest building. Then before that, the Taipei 101 was the tallest. Before that, I think before construction of the Taipei 101, it is Petronas Tower was the tallest building, and then before construction of the Petronas Tower, the Sears Tower was the tallest. So, Sears Tower constructed probably in the 1972, 73, 74. Supervisor of the structural supervisor, you may say it is that Dr. Khan, Dr. Fazlur Rahman Khan, and that building was the first building which involved this bundle tube system, and till today this bundle tube is somehow experimented or somehow implemented in various other improvisation definitely, but bundle tube is still exist. So, those are the Sears Tower, the left hand side photograph, the Chicago 108 storied. See, we thought of in the last lecture of 20 story, 30 story in the shear frame building, the frame shear interaction building may go another maybe 45, 50 floor maximum, but tube systems gives you go up to 80, 70, 80 something like that. Sears Tower bundle tube is 108 storied. Burj Khalifa may not be perfectly the bundle tube, but there are still some consideration of the bundle tube system, and there are some other type of structural philosophy has been actually followed. So, that was 163 habitat floors from Sears Tower 1973, 442 meter, we have reached almost about double of that, 828 meter. within this 30-40 years of time, or maybe a little more than that, 40 years of time. So, the future trend is the diagrids, exoskeleton and superframes. So, just in brief we will discuss that one. So, diagrids are we eliminate the vertical columns on the periphery, and we go with a diagonal kind of a member, which is called as a diagrid to carry the gravity load and as well as the lateral load, and these triangulations will create the configuration, and that is going to take care of the load. So, those are some of the diagrid structure. The exoskeleton is another type of structure, where we assume that the structural load carrying things are taken care of by the external skeleton. A skeleton, externally a skeleton has been prepared, which are the major take the major contribution to take the load in the facade. So, with the I have written over here this exoskeleton, that with associated with the conventional type. So, conventional, this inside is maybe the tubes or any other kind of the conventional shear core tube, tube in tube, whatever, but it will give another the externally a kind of a system is developed, which is going to take up that one till the much more height exoskeleton. Those are you see the first one is the Barcelona, the hotel building, which is a overthrow. So, throughout exoskeleton is created, and that create the external loading capacity of the building is increased a bit. The Burj not Khalifa, Burj Al Arab, which is constructed beforehand is in the Gulf, Persian Gulf in Dubai. It is reclaimed area in the Persian Gulf, in the Gulf, in the reclaimed area. This building has been constructed, look like the sailing boat, and the exoskeleton has been used. See, this particular structure is expressed, I mean the structural expression, it is actually the modernistic kind of a the movement, you may say, in the contemporary kind of architecture. So, structure is exposed, the behavior of the structure is also exposed. There is diagonal huge truss and all, which act as a two exoskeleton in the two sides of this particular building, wonderful building. And the super frames are it is also supported by mega columns in the four corners on the typical areas or the places where you require some kind of a mega columns, and based on that mega column the frames are constructed, but again I have written associated with the other conventional type. So, those frames are constructed with the mega, these are the mega columns, the sides, and there are frames after frame, which create a kind of a geometrical pattern in the building and infusing the conventional type tube systems also. So, one building from Venezuela, Caracas, this is the, but those exoskeleton and the super frames are still under considerations also. So, I think that is all for today, and these are the references. Out of the references, there are good references, these particular references I must tell you. The third one, this is a paper in Architectural Science Review. If you require, I can share, or you may Google it also. This paper is available by M. Ali and Moon, K.S. Moon, which actually tells everything about what I have just now told. It's the paper is probably the backbone of this two presentation, and cannot be supplemented. I mean, this is the wonderful research they have done, thoroughly the history of the development history of the structural systems of tall building. And this one is also one of the good book. This book is the last but one. This book was that book will give you lot of case studies about the high rise building. So, in conclusion, I must say that in high rise building structural systems, structural intensity in terms of the material used increase in as when it is go height, that is the premium of height, as Dr. F. R. Khan said, and exterior system of structure mainly depend upon the tubes. And the next lecture, the last lecture of our course, the 40th lecture will be on structural detailing in the next, and that will be our last lecture. Thank you very much.